In this module, we're going to talk about the effective area of an antenna. So this is a parameter that it relates to the directivity, which we described in a different discussion, and translates it into the key performance parameter that we worry about with an antenna, which is how much electromagnetic energy can it capture in the case of a receive antenna. So recall that when we describe a propagating wave, we usually talk about it in terms of its power density, which is E cross H conjugate or E cross H, and is in units of watts per meter squared. Now the effective area of the antenna is basically how much area the antenna electromagnetically has to capture this power density. So if it goes into this antenna, and this antenna has an effective area of something in meters squared, so this wave is coming in, this is the antenna, then the total amount of power captured would simply be the two multiplied together, right? So if you multiply the two together, you're left with the watts of power captured. So in other words, if we have our antenna, our electromagnetic wave coming over, and this has some kind of watts per meter squared, in the end, once you have your directivity, you can use that and translate that into how much actual area would we have available to capture this wave. So if this is meters squared, in reality, you might see that our antenna just looks like this little satellite dish here. It's maybe this big, but depending on how it's designed and what the directivity looks like, the effective area for the wave coming in might be some area that is different than what the physical area is. And so in the end, you can kind of see how, like from a solar cell or catching fish perspective, you can kind of visualize how you relate this to the total amount of power that you would be able to receive extract from that incoming electromagnetic wave. Now the main way to calculate the effective area is it is directly related to the directivity by the following equation. So the effective area is lambda squared over 4 pi times the directivity in the direction of interest. So when you're trying to figure out how much of your signal you're going to be able to receive, if you have the directivity of the antenna and you know what direction the signal is coming from, you take that direction in terms of theta and phi, plug it in here, and then multiply it by the square of the wavelength divided by 4 pi, and that will give you the effective area of that antenna for this particular incoming electromagnetic wave signal, radio wave signal from this particular direction. So if you look at this, it's worth noting that in general, the greater the effective area, the better, right? And so if you look at this expression, one of the things you might see is if you know what direction you're coming from and you have a high directivity, that's one way to get a bigger effective area. Now this relationship here between the effective area and the directivity is true for any antenna. And I think that if you just look at this, one other take home you have is that for the same amount of directivity that you have, the higher the frequency, so the shorter the wavelength, the smaller effective area it translates to. Therefore, if overall, for the same amount of power density, if you really want to extract the same amount of energy, meaning that you have the same effective area, as the frequency increases, the only way, lambda is going to go down, so the only way that you can really get the same amount of effective area and extracting the same amount of goodness from the incoming wave is you really need antennas that have a high directivity. And remember, directivity is averaged out by the average power. Therefore, the higher the frequency, the more you're going to have really high directivity antennas that really only work for the particular direction that's coming from, so that you can still get the same effective area and extract the same amount of energy. So that's one of the key take-homes, is that the higher the frequency, the shorter the wavelength, for the same amount of sensitivity and power extraction, the greater your directivity needs to be, which also means that you're not equally sensitive in all directions. So you need to have better beam steering or better control of being able to know where the signal's coming from, so that you can steer your high gain aperture in the necessary direction. And we'll see that in subsequent discussions of the link budget formula, or the Friis transmission formula.